All right. Good afternoon by 1 minute. I am now standing between all of you and lunch, as is typical. So hopefully we won't go over time. We got a nice hour-long slot, so we should be good to go. So I want to talk to you today about BPF Trace, and I'm kind of curious, like, who's actually used BPF Trace to do something? A few people. Okay. Who has never heard of it before and has no idea what I'm talking about? About half. Okay, that's awesome. Well, the good news is I'm going to give a really good intro to it. So if you haven't heard it before, then that's kind of okay. Incidentally, if you've been down to the bar in the lobby, they have a printer that will print on your coffee. So if you want to put your face, your daughter's face, your Ubuntu logo, or whatever on a coffee, it's like €4 down in the bar. So here is the BPF Trace logo on a coffee. I thought that was pretty neat. I'm not quite sure why, but all the BPF and tracing projects are using ponies as logos. Without color, it's hard to differentiate them, but supposedly the wispy details of this make just because BPF Trace is easy to use, but I don't really see it, but it is what it is. I've been in some kind of SRE role or support engineer role for the last 15 plus years, and that means that I'm often debugging systems and things that are deployed in software that I didn't write and I didn't configure. And so I frequently find myself needing to do some kind of either performance analysis or behavior analysis. And performance analysis being, some kind of performance counter. I want to know how many bytes or operations per second are happening, how much network speed's going around. Or if I'm speaking behavior analysis, I want to maybe understand why is something going wrong? What files are we opening? What steps are the program taking? Except I always need to do that at runtime and in production, rather than very often you just can't make some kind of simple reproducer. And so I want to be able to do these at runtime and in production. And if we look at our traditional performance analysis tools, so these are tools that are going to give us some kind of number. Most of the time, they're very fast, which is great, but they're using some kind of subsystem specific performance counters that are already baked into the kernel. So the original developers already figured out you need to know how many bytes a second are coming off disks and networks, and they keep some counters for that are super fast, but they have heavy use of averages, and those hide outliers. You very often can't dig in any detail. It's just you did 100,000 operations and they took 0.1 of a second. They also tend to be limited in their breakdown. So if we look at tools like IOStat or NFSstat, all these kind of tools listed, they'll tend to show us maybe everything per process or everything per disk, but you can't customize or expand that. You can't show it per disk per process in most cases. They also often have, in the case of netstat and top, for example, they're kind of an instant snapshot of data at that exact moment, and that can cause you to miss things. If you're running top, it updates every 1 or 2 seconds. If you have a bunch of processes that launch and exit within 0.1 of a second, those will not show up in top at all, and you'll completely miss all their CPU usage and other resource usage. And in certain scenarios, all these things can be a problem. And so if we look at examples of where these averages can kind of hurt us, this is IOStat. If you've used this in any kind of storage application, it kind of shows you reads per second and writes per second our IOPS, and it shows how many bytes a second you're doing. And it also shows us the average wait. So if we do a write, the average wait time for all these writes are doing 27,000 writes a second is 0.03 milliseconds, which is super fast, and that's super great. The problem is it might be they all took 0.03 milliseconds, or it might be that almost all of them took 0.01 milliseconds, and one of them took 5 seconds. And there's no way to kind of tell the difference with these kind of traditional performance counters in most cases. And if you've worked with storage, you might understand that. But if you haven't worked with storage, we can look at CPU. And I think this is something we can all relate to. And this is the output from top that I doubt many of us haven't used at least once. And I'm running FIO here. So I'm doing a storage benchmark. And it kind of shows in this column here that I'm using 100% of the CPU. And that sounds great. I'm using all the CPU. That's great. But then if we look up the top, it says we're only using 6% of the CPU. And it's 93% idle. And that it kind of doesn't add up. And if you haven't, I think I just stepped on something. I stepped on the HDMI cable. So hopefully that'll come back. 1 moment, please. Hey, that's better. So back to our, I've got to like now not step on that and not go in front of the screen. Excellent. What we don't really know if you haven't used this before is that this number here doesn't stop at 100%. It goes up to like however many cores you've got. So in this case, we've got 32 cores. It would actually go up to 3200%. And if you press the number 1, it will actually break it down for us. So top will show us like each CPU, like how much time it's using. And so in this view, I can see that one CPU is busy, and that's kind of why like those numbers didn't add up. But in all these contexts and these different tools, you can try and like, change views and everything, but we don't really have a generic way in every case to kind of like do this kind of thing. And these outliers can either be super great or super bad, depending on the situation you're in. And if we go to behavior analysis, so instead of looking at performance numbers, if we're trying to understand like step by step what a program is doing, or like what is going wrong when we open a file, most of these traditional tools will send all of that data straight into user space. If you're like trying to trace every file being opened on the entire system, every one of those events gets streamed into user space, and the overhead of that is quite high. And I'll go into that in the strace example in a minute. But they're all kind of like that. Bpftrace, it's a really powerful kernel subsystem. It can tell you like every IO request or every disk. It can show you like as it transits through the queues, goes through like DM rate and device map rate, all this kind of super powerful information. But it kind of just, it's a fire hose of information that takes up a lot of resources to generate, even if you're only interested in a small part of it. And even if you've just turned up the debug log level in any app, you turn like debug logging to 20, like it just has to be the only level that logs the 1 bit of info you want. But now you've got 10,000 messages you didn't want and like 1 that you did. We also find that sometimes there is just no like performance counter for some detail that we want. A lot of times they're there, but they're not always. So I talked about strace. Strace is one of my favorite tools. And it kind of like, it intercepts all the system calls that a process is making, like opening a file, accepting a network connection, reading and writing data in it, and it fire hoses all that out, including the exact data written and the number of bytes. But if we just look at the performance of that, so I'm going to use a contrived example that is to exaggerate the performance impact so that we can understand that on human timescales of seconds rather than like milliseconds. So I'm going to use DD to read from dev0. So we're just getting a whole bunch of null bytes. I'm going to write it to dev null. So we're reading null bytes and throwing them away immediately. A very useful action for a computer to do. But to make it contrived and extra slow, we're going to do that 1 byte at a time. Normally, we would batch these in like 4K or a megabyte or something, but we'll do that 1 byte at a time 500,000 times. So we're going to read and write 500,000 bytes. And if I just do that on its own, it takes 0.2 of a second. Not too bad. If I launch strace to analyze that process, and I actually, in this with except, I'm going to tell strace to only look at accept system calls for a network connection. Now, DD doesn't make any network connections, so strace is going to output precisely nothing from this operation. But just attaching strace to that process, that same operation goes from taking 0.2 of a second to 18 seconds. That's nearly 100 times slower. And that's an incredible performance impact that in production, we often can't incur, or even a risk of that may not be incurable. If you haven't used strace, this is kind of what the output looks like. If you haven't used it, you really should look at it. If you're not in like a production situation, it's super powerful for understanding what's going on. You can kind of see it kind of tells us, we've opened files, tells us, we're reading and writing these null bytes. These are the 500,000 null bytes I talked about. We read it from one file, wrote it to another over and over and over again. That's the kind of fire hose info. So if you do that 500,000 times, this is going to scroll down your screen for quite a long while. So why is strace slow? Like when I attach strace, why is it now 100 times slower? And the reason is that strace is using a mechanism in the kernel called ptrace. It's the same mechanism that a debugger like GDB uses, and it's literally a remote control for the process. So it's like getting a remote control for the process, and we go like, okay, pause the process. And so strace will make a system call called ptrace syscall. It says to the kernel, okay, I want you to run DD, and I want you to wait until it does a system call, and then I want you to stop it and let me know. So, okay, so we go into the kernel, and then we go to run DD. It runs the write to write one of those bytes, goes into the kernel, and the kernel normally here would write that byte for us. It would do that busy work. Instead, it now has to wake up strace, and DD's paused, so it can't do anything right now. And we then context switch to strace, and it goes, oh, great, we did a write system call. But actually, I want to know like how many bytes we're writing and like what file it's being written to. And to get that information, we actually need to look at the CPU registers of the strace process. That kind of doesn't come for free. So then we ask the kernel, hey, can you get me the registers for that process? Go to the kernel, we come back again. We've now got that, so we now know like what we're writing, where it's being written, and we tell the kernel, great, let's finish running that system call. So it goes back into the kernel, It writes the byte to disk or memory or whatever it's going to do, but then it traps back to strace again, and we have to get the registers the second time. And why do we have to do it twice? At the start of a system call, the CPU registers will have the arguments that are passed in. So the file descriptor, the number of bytes, etc. But we don't yet know the return or the result of that system call. We can't get that until the end. And so we have to interrupt it at the end to get the result of the system call. But at that point, the data we passed in as those arguments may have been clobbered or reused for something else. We can no longer see that at the end. So for every one of these system calls we probe, we have to probe both the start and the end in order to see both the arguments passed in and the results. So we get those, go into the kernel again, get those registers, come back, and then we finally tell the kernel, okay, you can like finish the system call and actually tell DD that you're done now. And so we've added 8 extra context switches in and out of the kernel to strace on top of the 4 that were already there just to trace it. And the entire time all this work is happening, DD is paused and can't actually complete any work. And so that is why strace is particularly slow. So wouldn't it be great if we could kind of like define some custom metrics that's maybe not already pre-written into the kernel? And it'd be great if we could kind of group those in some kind of custom way. So maybe we want it per disk, per process, or we only want to count them if it takes more than a millisecond, something like that. And wouldn't it be awesome if we could do that in a super high performance way that doesn't have the overhead of these kind of fire hose type tracing systems? And the good news is that we can do that. That's what we're here to talk about. And so I'm going to show a few example tools just to kind of give you a taste for what you can do with BPF Trace. And so this first tool is get host latency. And so what it's going to do is trace every process on the system. So not just one, but every process on the system. It's going to trace when it's doing a DNS lookup and tell us the process, what host it's looking up, and the latency of that request. And what's unique about this is that we're getting to see individual operations. So it's not just like an average. We can see the individual operations per process, and it's also system-wide. So we're not getting it like only from one process with strace or GDB or something like that. A time when I've used tools like this, I used to do a lot of work in web hosting, and WordPress is a very popular and wonderful tool for publishing websites. The core code of WordPress itself is pretty great and fantastic, but you can write plugins for WordPress that are written by like millions of developers who don't necessarily are not all the best programmers, and people tend to add like 20 or 30 of these things that all run for every single web request. And a lot of them will end up fetching resources from the internet in some fashion. I'm from Australia, and Australia is a long way away from everywhere. It's 200 milliseconds, 0.2 of a second to like any request to the US or Europe. If you can't tell that from the latency, the fact that I'm wearing shorts in winter is probably a giveaway. But so, you know, some of these tools, when you run them on like a US web server, they wouldn't be that slow. It might take a second to render the website, but like that's kind of okay. But you run it in Australia and it takes 200 milliseconds every time it does something. And suddenly like you're waiting 10 seconds or 20 seconds for your website to load. Here's another example called UDP Life. So this will show us before we're looking at DNS requests. Now we're looking at any kind of UDP connection. Every time we send and receive a packet, it kind of shows the latency it took from when we sent it to when we got the reply. And it shows it again for every process on the system. So we can see the process name like wget. We can see the local and remote address, the port number, and like the milliseconds, the number, the actual latency of that took. In this case, we actually see mostly DNS requests here, but also this is like an NTP request. Here's another example called OpenSnoop. And so this is looking at like for every process on the system, what files are they opening? And then like, was there an error when that happened? Cases where you might use something like this, like strace is really good at this. If you're not performance critical, that's like probably the number 1 thing I use strace for. But so far, like all of these tools are still like fire hosing information. So we're still seeing like every file opened and like every kind of request still getting kind of streamed back to the tracing tool. So another kind of powerful thing we can do with BPF Trace is we can actually summarize things in various different ways. So here's an example of a histogram. So this is showing IO latency. So currently for every request on the system and every IO request, like how many of those took 8 to 16 microseconds, 16 to 32 microseconds, it kind of buckets them all up. And so we can see here, the vast majority of the operations are pretty fast, like 8 to 100 actually microseconds, not milliseconds. So that's super fast. But for some reason, one request down here took 1 million to 2 million microseconds, which is actually 1 to 2 seconds. Why is it taking 1 to 2 seconds to get something off the disk? That's kind of crazy. That shouldn't really happen. And if in this example, which is from a real case I was working on, that 1 to 2 seconds, like these are all sequential IO operations. And so it doesn't matter that like 30,000 were fast. That one that took 1 to 2 seconds, this whole operation now took 1 to 2+ seconds to execute that normally would expect to be very fast. And so that's the kind of power of the like histograms and summaries. And I can then ask BPF Trace to maybe show this per process or per disk or in some custom way that we couldn't get out of the other tools, and with a very small performance impact. This is just another example showing like system calls per process. And in this case, we can kind of like categorize things in two different ways. We can kind of categorize how many system calls happen by the kind of system call and how many happen by which process, like how many total system calls per process, and we're like counting those at the same time. So what actually makes this possible? So the first thing that kind of made this possible is actually quite an old technology at this point. It was the Bpftrace subsystem in Linux, which was added in 2008. And what it kind of brought that was kind of powerful was you could dynamically instrument various parts of the kernel and generate some kind of event. And there are a couple kind of key events I'll talk about initially. The first one is a static trace point. So like if a kernel developer of like the network subsystem or the ext4 file system knows you might be interested in some kind of event, they can add like a named event. And here's some examples, like a block IO request being queued or completed, or a lock being taken, or transmitting a packet. And these are kind of static, so they don't change between kernel versions. And they also like pre-calculate some useful information, like what network interface or how much data, etc. So we have these static trace points, but if the developer of that system hasn't added one, like a trace point for information we want, we can also just probe literally any function in the entire kernel and kind of just inspect that. And so we can kind of make our own path, figure out how we want to count things. In the kind of initial, when we were using Bpftrace on its own, if you use one of these trace points, you kind of got that extra context. But if you use the kprobe, you knew that particular kernel function was executed, but you had no context. You didn't know which network device or file or what data was being sent, and you couldn't really get that extra information unless it was already a trace point that was added. Now, this kind of sounds expensive, the fact that we can probe like every kernel in the system, and you would think that having that enabled within the kernel would be quite high overhead. And the reason that it isn't is because the start of every kernel function has like a little instruction in it that jumps out to this tracing code to check if I'm being traced and like collect the appropriate data. But at boot, when the kernel boots, it actually overwrites all of that code in every function with like no ops, just like tells the CPU to do nothing. And CPUs are really fast at doing nothing. They've optimized that like crazy. And so even though you've got these like 4 or 5 instructions to do nothing, like the performance impact of that is not really noticeable. And it's only when we want to trace a specific trace point or a specific function that the kernel will then write those like few no-op instructions back to the actual code to jump out to the tracing subsystem and actually trace that particular event. And so that's how that infrastructure is enabled on every kernel today. On every machine you're running, it's all enabled and it's all there, and you can turn it on at runtime. But unless you turn it on, you don't really notice that it's there. Incidentally, it's just kind of similar to how live patch works. It kind of does a similar thing. It detours out of the function in that same sort of space. The next thing that was kind of powerful is when we were doing things like strace, we were synchronously kind of going in and out of the kernel and the tracing program and transferring that data synchronously. And so when Bpftrace came in, we now have a ring buffer in the kernel. And so the Bpftrace system kind of knows that we have a trace point. It already knows all the data it's going to gather, that we've run this function, or it has those statically defined trace points to collect information. And instead of having to transfer that information out to user space like inline and wait for that, it just puts it in a shared memory buffer that the kernel can kind of write to, and then the tracing tool can read from on like 2 different CPU cores. They can kind of run in parallel and not really interrupt or wait for each other. And that brings the performance, it makes that performance much, much better than waiting on the tracing tool. And so because the kernel does that all in kernel space and it doesn't context switch, that makes it much faster. However, it also means that like the tracing tool can't customize the information it's reading. It can't read some extra memory or something like that. And so it relies on those, at least in the initial implementation, relied on those static trace points to kind of predefine the information you wanted to know. And that's what we were trying to get away from. We want to be able to customize and write our own programs. We're also still transferring all this information to user space. It's going through a shared memory buffer, and it's kind of happening in parallel, so it's much faster, but it's not as fast as it could be. What is mostly a good thing is if that buffer fills up, the events just get dropped. That's great because you're in like a production kind of environment because your system doesn't get slowed down. It does also mean you miss some events. So it's kind of a downside from a tracing point of view, but most of us would prefer our system to keep running than to like stop running because we couldn't keep up with the tracing. And even if that data collection is like taking too long, the kernel also has mechanisms to like just start like dropping events if it's just spending too much time on all of this kind of tracing work. So if you look at the performance of this, so in our first example, it was taking us like 18 seconds with strace doing nothing. If we use Bpftrace, which is a rough analogy to strace, it doesn't quite give all the exact same information, but it does a lot of similar information. You can see data being read and written. If we use Bpftrace on that same DD command, it now only takes 3 seconds. That's like 5 times faster. That's already a dramatic kind of performance improvement. We can then further tell Bpftrace that we're only interested in the write system call specifically, if that's all we're actually interested in. And if you remember up in the strace land, like it didn't matter that we weren't interested in anything that happened. It still slowed us down like 100 times. But with perf, you know, once we only look at write system calls, now it only takes a second. So we're only like 5 times slower than we started with. That still seems like a big impact, but it's way, way better than we started in the strace kind of case. But even now, we're still copying all this data to user space. So when we capture those 500,000 write calls, 500,000 events that a write happened are all still sent to user space. And that's kind of where we're still losing a bunch of this time. And so we can do better than that. And so that's where BPF comes in. And so BPF was first added like in the 90s as a way of filtering packets. So, you know, if you want to TCP dump an interface and you're interested in like SSH traffic, which is usually like quite small part of all of your traffic, the naive implementation would be to send every packet, you know, out of the kernel into TCP dump and kind of parse that in user space and like skip over them if we're not interested in them. To speed that up, they added BPF, where we would actually send like a tiny little program in kind of like BPF assembly. It's not quite the same as like x86 assembly, but it's kind of similar conceptually. It would send a little program into the kernel that it would then parse those packets with and do that in kernel space rather than have to switch out to TCP dump. And so if the packet didn't match this little program TCP dump wrote, we would never send it to user space and never parse it out there. And that would speed up packet dumping considerably. In about the 2013 timeframe, that was expanded with what was for a while called EBPF. And it's kind of related, it's kind of similar, but in practice, like it's a totally different implementation. But they added like, you know, more word size, more storage, more registers, and they started JIT compiling it. So in the earlier implementations, it was like an interpreted language, whereas now we're kind of compiling this EBPF kind of assembly into actual machine code at runtime to run like super, super fast. Putting custom code into the kernel at runtime sounds kind of scary, and it is kind of scary and continues to be a little bit scary. But one of the things that eBPF has that makes that kind of work is that there's a verifier that actually parses that program and tries to make some guarantees that it's not going to read unsafe memory, it's not going to crash, and critically, it tries to bound how much time it's going to take. Because even though these are super fast, like compiled tiny programs, they're still in line in like the network request path or the IO request path when we're tracing. So we still want them to be super, super fast. And so the verifier kind of enforces some limits so you can't have unbounded infinite loops and things like that. This obviously imposes some constraints on the kinds of programs you can write. And so there are some kind of operations we can't do with those limitations. And so the kernel also has some little helper functions we can call out to do things that you can't do natively in BPF, to maybe convert a C group ID to its path, or like a whole kind of bunch of things like that. And so the real power comes when we combine these two things. So when they added eBPF, they also added many more events that we could attach these programs to. And so instead of just attaching them to network packets, now we can attach them to one of those trace points or to a K-probe for every time a function runs, and a whole bunch of other sources. And so now this kind of summary or analysis of data, we can push a program into the kernel that's super fast. There's no context switching. And we can customize exactly what we want to summarize on our own with a program that we wrote, rather than something that a kernel developer set in the past. So if we look at the performance of that, so in this case, I've now written a very simple BPF trace program that is going to probe every one of those 500,000 writes, but instead of like returning every separate write to user space, I'm just going to add up how many bytes were written, and only that one number of 512,000 is actually sent out to user space out of the kernel. And now our performance, our speed is up to 0.3 seconds. So we're now like only 50% slower than our initial case, and way, way, way faster. And if that's all we wanted to know, that we wrote 500,000 bytes, then that's all we need. But if we were using strace, we never had that ability to kind of cut down how much work we were doing. It was like all or nothing. And 50% kind of sounds like a big overhead still. In practice, because this is a contrived example where we're only writing 1 byte at a time, we spend much more time in like the overhead of system calls than compared to doing actual work. And so if we look at FIO, for example, that's a storage benchmarking tool. If I run an actual FIO test with 32 kilobyte buffers rather than 1 byte buffers, as a simple example, I can get 34,000 IOPS when tracing it, and I can get 37,000 IOPS without any tracing enabled. And so that's like an 8% performance hit. And in practice, you can usually get it sort of even better than that. And that's the typical performance impact you would see is certainly less than 10%, often sort of less than 5%. Okay, so let's have a little look at the BPF Trace language. So I haven't really shown you this yet, but these BPF Trace scripts are custom scripts that someone can write kind of, you don't really even need to be a software, like proper software engineer or like a kernel engineer most of the time. They're quite accessible scripts, and they kind of look like this. If this looks familiar, it's inspired by the dtrace language, which is a Solaris tool from Sun Microsystems in the mid-2000s that does basically the same thing as BPF Trace, and it was inspired by awk. So they're kind of effectively awk scripts if they look familiar. And so as to do a little tour at the start, we have like a begin stanza, so we can do some work to kind of set up. In this case, I'm just going to print a string. We can match a probe. So the probe type is, like I talked about, like a trace point that's predefined, or any kernel function or any function in a userspace program. So I say the type and name I want to probe, and then we have a predicate, which is basically like a condition. So I only want to match this probe if it's a Python process in this example. We then have a couple kinds of variables. So in this case, anything that starts with an @ is global. If it starts with $, it's a local variable. So I'm going to create a global map, which is like a hash or a dictionary indexed on the thread ID. And I'm going to store the nsex as like an internal. It's just like the time that that event happened. And so in this example, I'm going to probe one event. I'm going to see what the time was when that event happened. I'm going to probe another event and then see what the difference in the time was to calculate the latency between two different events. And so I calculate that, and then I'm going to store that. So in between those two probes, I calculated the latency. Now I'm going to store per process ID. I'm going to sum up how much the latency was in that event. And so at the end of our program, every 30 seconds, and at the end of the program, we're going to print out how much time in total we spent, the total latency between those two events we probed, broken down by process ID in this kind of simple example. And so here is a bunch of kind of one-line examples of BPF Trace programs we can write that fit in one line. In this example here at the top, we're going to look at how many files are opened by process. And so we want to trace the open system call, and we're just going to print out com is the process name and the file name argument. Because this is a trace point, we have these kind of predefined arguments kind of passed in we can print. In this example, we're going to trace all system calls, so not just the open system call, but just any system call, and we're going to count per process name, so like Python or apt, how many of those we called. In this example, we're going to trace the read system call when it finishes, and we're going to sum up how many bytes were read. So per process type, by Python or apt, how many bytes we read in the time we probed it by using the sum function. We can do the same thing, but with a histogram. So a histogram of like how many bytes were read each time, and so on and so forth. So a bunch of like little examples of kind of one-liners you can do. You can also write much bigger scripts like in the first example. I'm not really going to cover them today, but if you get really deep into the tracing system, there's all kinds of events you can attach to. So we have these trace points and K probes I've talked about so far. There are U probes, which attach to user-space processor functions rather than kernel functions. And there's a whole bunch of like hardware events you can trace, like cache misses and all kinds of crazy things that I haven't really dug into. And if those things excite you, go read into them. There's lots of cool stuff you can do. But the main things I've mostly worked on is either a kernel or user space probe or a trace point. So I promised at the start 5 recipes for problems I've solved in like actual BPF Trace scripts. And so that's what we're going to look at now. So like some examples of stuff I've actually used in things I've done day to day. So in this first example, I was working on Juju charm deployment, and I want to like profile how long all of the charm invocations were taking. And it wasn't super obvious to me. Perf can actually see the call stacks and stuff of like C programs and C++ programs, but it can't do that for Python. But there is a tool that can do that called Austin, and it's like a Python profiler. And so I wanted to launch a copy of the Austin Python profiler against every Python process that started. And I didn't have a super easy way to do that, like by modifying the code. So I just wrote a BPF Trace script that every time a processor was executed, if it was a Python script, I would then execute and like open a copy of Austin, the profiler, in the background. It's a little bit hacky, but it works super well. I profiled every invocation of Python and got the results that I needed. In this example, this is actually a built-in tool that ships with BPF Trace called BIO Snoop, and it shows you like every IO request to a disk, including like the process that made it, the process ID and the disk, and the latency. But what it did not have was the offset into the disk and the length of that request. So I actually took the like example script and I added to it the ability to show me the offset and the length of those requests. And that's kind of like the power of these kinds of tools. You can kind of start with something else and add some information that you wanted that wasn't already there. As a warning, however, this particular tool, there was no trace points for it, so I had to use kprobes, which means you have to like trace all the kernel data structures yourself. And the block subsystem is kind of complicated, and I'm not really a kernel engineer. I kind of like pretend to be one occasionally. And so I did follow those structures incorrectly and get results that were correct most of the time, but not all of the time. So I would recommend, if you're getting to the level of kprobes and stuff, to like verify that what you're looking at is actually correct. And that's actually how I discovered I made the mistake. I started like running some commands, doing like known just DD to a certain offset and made sure it was correct, and like they weren't correct. And so that's how I kind of figured that out. So you do have to be a little careful if you're in the kprobe world, but if you're using the static trace points, that information is usually pretty reliable. What I ended up doing in this case I used this on was then further customizing the script only to output for a specific process name that Ceph was using. And so I was like filtering that information to only be Ceph and to show me those offsets and links. Here's another example. So we're going to look at IO latency, so how long each request was taking, and we can see that in IOStat, but IOStat does not break that down by process. So in this script, we actually index it with com as that process name, like Python or apt, and we get all that latency, but broken down by process. And what I was able to see in this case, this goes back to that example earlier where one IO request was taking from 1 to 2 seconds out of like 40,000. And that was a Ceph case I was working on. And I was able to see that that particularly slow IO request was only happening from this particular thread of Ceph. And that kind of started to narrow me in on like where the problem was, as I was trying to figure out. I knew there were slow IO requests, but I didn't know like why and when and how. And I kind of started with that latency script that showed me I had a slow request. I then kind of had a script like this that started to show me like, well, I now understood which thread was making it. And I was then able to dig in further into that particular thread of Ceph and understand why those requests were slow. Had another case where a Juju charm was executing a program that was supposed to stay running in the background that was getting killed at random, and I didn't know what was killing it. It was a murder mystery, and so I just traced every time a signal was generated, which process ID was killing which process ID, so I could understand why. It turns out it was systemd, so I then had to figure out why systemd was killing the process, and it was some complicated session scope management thing that I can't quite recall now. But the fact that I could see that systemd was the one killing it meant I could go straight to systemd, turn on its debug logging, and figure out why it was killing it. And that, it pointed me in the right direction to look. The last one, this is kind of one of my favorite ones because it feels like you shouldn't be able to do this, but you can. So you can, if you've ever, before SSL was so ubiquitous, if you wanted to see what a program was doing and you use like strace, you would see all the bytes that would read and write on the network. The problem with SSL is that all you get is a bunch of encrypted gobbledygook, and you can't really see like what the HTTP request is or whatever. And so this tool uses a uprobe, so we're not actually attaching to kernel land, we're attaching to the libSSL library on every process in the system, and we attach to SSL read and SSL write and actually get the unencrypted data as it's before it's encrypted or after it's decrypted, and print that out for every process on the system. And so if the tool you're using, which is what happened in this case, it didn't have an option to turn on, some things like Apache and such have like an option to turn on this kind of, unencrypted info. And I think like Firefox will like export the SSL keys, so Wireshark can like later decrypt them, but I didn't have that for this tool. And so by just intercepting libSSL, I could get the decrypted data. This does unfortunately highlight a limitation of BPF Trace currently, in that you can only print out 200 bytes at a time, just due to the way it's kind of working and using the BPF system. That is a limitation that can be fixed, but no one's fixed it as of yet. So if you actually want to do this, someone wrote a tool in Golang that also uses BPF, but bypasses that limitation of 200 bytes. And there's a link to that there. Now, there are a lot of people in this room, and I'm sure for every example that I gave you, you've probably gone like, I know there's a way I can do that. Like, for example, top, it misses short-lived processes. There is a tool that fixes that called atop. It uses the Linux accounting subsystem to get like every process that starts and finishes. But the point of like tools like BPF Trace is like, they're kind of a generic, you can do everything with one tool. And so like, you don't have to resolve every problem with a unique tool. that's kind of complicated every time. Like to write atop, whoever wrote that, I guess had that problem at some point in time. But with this, you can kind of very agilely, as like a non-kernel engineer, kind of dig in good enough. And that's kind of the point. So even if you think every example I gave, you have like some contrived way you could have done that kind of fast, there probably is, but you kind of always have to search for that and hope that someone's already written it. It was probably a couple thousand lines of C that would take you much longer to write than it would take you to write a BPF trace program in many cases. It's also reasonably systems administrator friendly or SRE friendly versus like kernel engineer friendly most of the time. Like I said, careful when you're chasing data structures and make sure you're kind of reading the right thing. And there are a few limitations, sadly, of BPF Trace, like that 200 byte length limitation. However, the same techniques that BPF Trace is using and making accessible, you can use in Python and using Golang. And there's a whole ecosystem of tools people have written, or if you have some complex use case, you might be able to then go write maybe a more complex tool in another language that kind of does what you need to do. And so if you haven't seen this before, this is just kind of like a smattering of some other tools that may interest if this kind of thing excites you and you haven't done it before. And I've got the slides linked at the end. If there's anything you want to do where you don't need to kind of customize or summarize or whatever, you just want to firehose info out, perf will actually do a lot of what you need to do without a script. You can just use perf, pass it some command line arguments, and it can do a lot of stuff kind of even without a script. So it's pretty powerful. Don't overlook it and assume you need to write a BPF Trace script. System Tap was kind of like a predecessor for Linux to BPF Trace, which is much more mature and has a lot of those limitations removed. It also works by like custom compiling and inserting a kernel module and doing a lot of magic that's a little bit scary, but it works reasonably well, so it might be an option for you. And dtrace, which is what this was inspired by, Oracle actually ported that to Linux, and amazingly released under like, actually the kernel part is in GPL and like the public part is in something even more free than GPL. I think that's like the only project out of Oracle that is under licenses like that. They've actually ported dtrace to use BPF internally, and it can almost do as much as the original dtrace could. So if you, again, that's another place you might better look. And if you've never looked at flame graphs, to this awesome way of like showing how much time you spent in different functions, and you should check those out as well. People are also kind of going crazy with BPF now that we can kind of jam code into the kernel. Everyone's getting very excited about it and doing lots of wonderful and horrible things with it. And so people are doing like network load balancing, CPU scheduling, firewall processing, auditing, like security auditing, all kinds of crazy things with BPF. And so again, if it sounds interesting, you can just go Google like BPF. And there's a whole ecosystem of things around this same kind of core technology, but for different purposes that's kind of forming. If you prefer, I'm not the best person at reading books. If you prefer book form, Brennan Gregg has a couple of really, really great books that go into much more detail. And if you want to go into much more low-level detail than I did today, there's a whole bunch of talks on YouTube. Just search BPF Trace. It'll give like much more complex examples and dive in a lot deeper than I kind of wanted to do today. And so that's it. With that, I would open up if anyone has any questions. If you want these slides, they're available on my website at this link. And if you want to follow me on Mastodon, the link is there. Microphone.
What's the simplest way to enumerate trace points, find out their documentation and parameters?
That is a great question that I should put in the slides. So BPF Trace-L will print out most of them. And there's also a perf list. So, but BPF, if you're using BPF Trace-L will print all the trace points, all the k-probes in just a giant kind of list. That's probably the best starting place. Out the back.
So some of the tools that you show there are some that come with the packages, right? And I noticed that there are usually two versions of them. I wonder if you could speak about that. For example, there is exec-snoop.bt and exec-snoop-bpfcc. And likewise, we have those two packages in a distro. We have BPFCC tools and we have BPF Trace. So what's kind of the difference? In my experience, sometimes one of them works and the other one crashes.
Yeah, so before the BPF Trace project really got semi-mature, there was BPFCC tools, and it was a set of the same tools but written in Python. So they had like the userspace part was Python, and they had like an embedded C program that does the kernel side part and kind of mixes those together. And that kind of came before BPF Trace. So those -BPFCC versions are like written in Python and C combos versus being written in this domain-specific language of BPF Trace. Even though they have the same names, some of the due to some of the limitations of BPF Trace, some of those Python versions actually are more advanced. It can do like more things. And so that's kind of why there's those two versions. And then even within BPF Trace, sometimes there's a version that uses K-probes. But as I mentioned, the K-probes, the kernel functions and layouts change over kernel versions. And so sometimes there's a version that uses K-probes and then a version that uses trace points. But the trace points might have only been added in kernel 6.0. And so like they have the K-probe version for older kernels and like the trace point one for newer ones. And if they crash, it's probably because they're K-probe based, would be my guess.
And is this also related to talking about what you said before about troubleshooting in production, about how invasive this troubleshooting can be? And BPF is much easier, yes. But what you need installed on the system extra? Do you need kernel headers all the time or just for one of these two packages?
That's a good question. I didn't really touch on that, and some of the other talks go into some more detail. In the earlier days, you would need debug symbols to do the K-probes, not to do trace points. But that's actually been fixed in your kernels. I don't know from which version, like 5 something. There's this thing called the BPF type format where the kernel has built in like all the kind of a mini version of debug symbols that lets all the BPF trace stuff work. So if you want to use BPF Trace specifically, you just need to install BPF Trace, and like I don't think you even need the headers, at least on a new enough kernel, because it uses all the BTF stuff. So you pretty much just need it. I think it does still. I'm trying to remember. I think it's still. I can't remember if it now embeds a C compiler or whether I think it still might rely on GCC or something. I can't quite remember. There was a project to get rid of that, and I think it might be internal now. So I'm not 100% sure. I'd have to check on that.
Have you found yourself needing to install extra dependencies when you were troubleshooting production systems?
So when I'm using BPF Trace, I just installed that one package and that's it. It doesn't really pull in a lot. So maybe it doesn't need GCC, yeah. In the newest version, I'd have to. It's very dependency light. There was also a snap of it for a while, but it's currently not published. So that was like even easier because it didn't pull anything in, but you know.
If you had snapd on that system, yeah.
Right, yeah. Okay, well, thank you very much. I hope that was helpful.